All right, so, excuse me. So we're about a week out from the exam. In fact, there's only no fall break is this weekend, but this is terrifying to me to see only this many people here because I know what happens to exam grades when people don't show up. And I can guarantee you there aren't going to be any do-overs, makeups, curves like on this exam. So, let's try to be really intentional kind of this next week, kind of preparing ourselves for it. So one thing that's good to kind of go back through and do, first of all, we've still got, where is it at? There it is. That quiz, which is due at the end of the day tomorrow. So you kind of got those practice problems to look through. Once you have all those quizzes, you should be able to go back and review the results. I would use those quizzes to study for the exam. So those questions will be pretty representative of the types of multiple choice questions you could see. So I think I don't have the exact breakdown, I'm still finalizing, but the exam is going to be about 10 multiple choice questions and about 5 short answers, but they might have multiple parts. So it might be like, question 11 might have A, B, C, and D, right? It might have like 4 kind of components to it. So more of the points are going to come from those short answer questions, right? So even though there's like a smaller number, each question is like 4 or 5 questions potentially. And they're also going to be like short answer. There's going to be kind of more points associated with those short answer questions. So for the multiple choice part, reviewing these quizzes, are a good way to kind of think about types of questions I'll ask you. Now, also these quizzes, even though they're multiple choice, a lot of the times, some of them are short, like fill in the blank, calculate a value. So a lot of those will be similar to what you kind of have to do in those short answer questions. So those would be really good study tools. This midterm practice exam, I've got the formula sheet that you'll have up there. So kind of look, I got it updated from last class. I think I might have pointed out there's a few parentheses that were out of order. Kind of add in that test or that F statistic down here. So everything, this exact formula sheet I'm going to print out for you once we take the exam. So you'll have that there as well. We'll work through some of this midterm practice exam probably today a little bit, but for sure on Tuesday. If you guys have already looked through it and you have any questions, I can definitely start with those. Otherwise, I have another data set that I brought that I'll just kind of use. We'll kind of use data. I'll kind of think of different types of questions that I could ask you related to this, just different type of data sets, seeing more examples I think will be beneficial. So anyone have questions over specific problems on that practice exam before I if not, I'll probably just dive into that problem set, which, did I put it? I thought I put it up here. Let's make sure. I might have just forgot to add it to the home page. Should be in here. I accidentally put it. Well, maybe it didn't upload. Let's make sure it's in here. So I'll just drop it into the files for today. Probably move it to week 6. So we've got, here it is, that life expectancy.dta folder. So if you want to follow along, kind of download this, put it in your OneDrive. We'll open this up in Stata and kind of work through some examples with this data set. Like I said, unless there's any specific questions on this practice exam, I can start out with those. Yeah.
I actually have one question.
Mm-hmm.
Let me just make sure. Okay, so it's about like question 15, but
Okay.
the whole progression.
Mm-hmm.
So since you admit sophomore is like the baseline sophomores because if they have to be.
Yep. So if I have a kind of group of dummy variables that represent something, then I have, like, say in this example, I have 4 groups. And if I included all of them, I would have what? Term limit multicollinearity. So I have to leave one of them out. So I have to leave off sophomore here. So every coefficient in this regression is essentially telling me, let's think about, here we go. Oh, all right. So I've got, what was it? Free throw made. I've got an intercept. This was freshman, junior, I'm abbreviating here, but senior, right? Yes, here I'll write in senior sense. What was the group we left out? Sophomores, right? So every single one of these coefficients on these dummy variables is the additional predicted change, increase or decrease in whether or not the free throw is made from belonging to this group relative to the group I left out. So every single one of these coefficients, I should have actually done this, right? It's all relative to that group I left out. So in that example, all of them are negative, right? Which is telling me the probability that they make the free throw is lower if they belong to any other category other than the sophomore category. So what group has to have the highest predicted probability of making a free throw?
Sophomore.
That group I left out, right? Now, if one of these had been positive, so just to kind of play around with this, let's say this was something like that. What group would I know has to have the highest free throw or probability of making a free throw now?
Freshman.
Be the group that has a positive. What if it was like this? Now it's not freshmen. Freshmen do have a higher predicted probability than sophomores, but seniors have an even higher predicted probability. In fact, if these were the numbers, what would the difference between a freshman and senior be? So the predicted probability or the probability a free throw gets made goes up by 4 if they're a freshman. It goes up by 16 if they're a senior. So being a senior relative to a freshman, how much more would that probability you make the free throw go up by? Being a senior increases it by 0.18. Being a freshman increases it by 0.04. All I would do is take the difference between the two, right? So there would be what? 0.18 minus 0.04. The probability that a senior makes this free throw is predicted to be about 0.14. The probability that they make is 0.14 higher than that freshman category. So even if I want to make comparisons to groups that are both included in the regression, I can still do that using their coefficients. But each coefficient is always relative to that group I left out. We just have to leave one of them out because I can only be classified as one of those 4 categories. If I try to include all of them, I don't know if I did this in class or someone during office hours, but it might be worthwhile. So let's just in general terms write this. So let's say I have something like this, where X1, so let's say I know instead of like 4 categories, I have 2. I'm either over 65 or I'm 65 or younger. Well, if X1 is going to be over 65, then I could rewrite that as, well, if I have this 65 or under second variable, I know that anytime X2 is equal to 1, this has to be equal to 0. Right? So I would think about this as, so how could I rewrite this? It would be 1 minus X1, right? Anytime someone's over 65, they're automatically going to be not 65 or younger, right? Why I left out that specific group. So you can leave out any of the 4, right? So the reason why, just to kind of be complete with this, and then I'll kind of come back to your question. Really, if I tried to include both of these variables in my regression, what am I really doing? It's actually like I'm just using that same variable, but now it's got like multiple coefficients. And so Stata doesn't have a way of reporting this, like combining those total effects. If you wanted to do the matrix algebra by hand, but Stata can. So here, really having information on X1, X2 had no additional information, right? It was a direct linear, we'd say linear, it was a direct relationship with this other variable. So we need to leave one of them out. And then our comparison is always just going to be then to the group we left out. So the reason why here I left out sophomore is I wanted to give you an example where all the coefficients are negative. Because that makes it a little bit easier to identify, well, if all of these are negative, it must mean that the comparison group had the highest probability. What was our comparison group? Sophomore. But you can leave, in practice, I think, I'm not sure there's a question on here, but if I gave you a different one where you had some positive and some negative values, So this example, what group might it make more sense to leave out here? So up here, I've got, let's say I saw the coefficients instead with 0.04 in freshman, negative 0.21 junior, 0.18 senior. Typically, we said best practice, I want to leave out which group? Lowest or high. So here, what would kind of be my two that I would choose from? Probably either want to leave out junior or senior, right? Senior would be the highest predicted. So if I left out senior, what would all my coefficients become? If I left out junior, all positive. Perfect. I'm liking those responses. This bodes well for the exam questions that I have about this, because there's something similar to this, okay? Any other questions on that practice exam, like I said, before I jump into kind of the additional example I think about, I brought it today. Okay, excuse me. So I've got an open, whoops, got just a blank do file. I said you could download that life expectancy, drop into your OneDrive, and we're going to kind of run with this. So I'm going to try to kind of show you best practices here. So in case I want to do this again, saving all of my code, I'm going to put in, if I had data open, I would have had to clear it out. So I'm going to look at this data set. It's got a bunch of different stuff in here, right? So it's basically a bunch of different countries. Oh, sorry. Thank you. It's now I'll walk through that again what I did. All right. So I had data. I went and I opened up that life expectancy file. I just copy and pasted it over here so that I had it if I wanted to use it later on. I'm going to widen this up to make it look a little bit nicer as we go. So I've got all of these different countries. I've got the year. I've got their infant death rate, polio rate, GDP per, I think actually this is just total GDP. So I've got a bunch of different variables here, right? So maybe I want to try to predict something like, let's see here. So we got this life expectancy variable. So maybe I'm going to try to predict life expectancy. And I'm going to do this based off of, well, there should be some measure, I think, of income here. Let's see. So we don't have income, but what we do have is this GDP variable. So I could include GDP, right? And also, I'm going to include the population. Yeah.
Where did you put that data set?
So I just put it under the files tab, so it wasn't in any folders. It should be kind of, oh, am I in the right section? Yeah, right. So life expectancy.dta should be right underneath the syllabus. Here, I'll add it.
Oh,
Yeah, just to make it easier too, though. If anyone else is still hunting around for it. I'll add it to that week 7 exam review. Okay. So I'm going to think about, well, actually, I can kind of do this in pieces. Let's just try to predict it using GDP. Now, before I even run this regression, because I actually have the GDP measure, think about what that coefficient estimate is going to be. It's going to be the effect of what? A 1 unit increase in X. So here, if I have GDP measured in US dollars, what's the size of that coefficient going to be? Do you think the effect of having $1 more GDP on life expectancy of the country is going to be? It's $1. Yeah, it's so small, right? So I'm expecting e to the negative something here, right? Sure enough, e to the negative 12, right? I'm moving that decimal 12 places to the left. This is the effect of $1, right? So kind of to highlight some things here. So what might make more sense for that GDP variable? So I'm going to generate a new variable, call it GDP reg, where it's going to be a little bit more useful to interpret, right? So GDP we see measured in, I mean, not just thousands, not hundreds of thousands, but even like millions, right? So I'm going to take $1 million and I'm going to scale my GDP variable by dividing it by a million. So now my new GDP reg variable is basically GDP but in millions, right? So every 1 unit increase will now represent a $1 million increase in GDP. So what is likely going to happen to the size of that coefficient? Yeah, it's going to go, well, it's going to shrink. No, right? Yeah, so if I think about, if I now use this variable after I scale it, now a 1 unit change will not represent a change of $1 GDP. It's going to represent a $1 million change. So that coefficient should be larger. Now, if I scale variables, right, you think about when I'm calculating the variance and everything is scaled, what should happen to my statistical significance? Nothing should happen, right? In fact, what should happen to my R squared? Nothing should change. So let's see, maybe I'm full of it, right? But let's do this, kind of compare. So I had an R squared of 0.04 before, 0.04, oops, after. That test statistic is still the same, right? Everything here is kind of still the same. Now, what is different, I'm now no longer having e to the negative 12. Now it's only e to the negative 6. Well, maybe I didn't scale this enough, right? Because $1 million changes in terms of GDP is still relatively small, right? But, you know, for the sake of this example, let's go even further, right? So I'm going to drop that variable. And instead of a million, let's do billions, right? We'll see if we get something that at least looks a little bit more manageable here. So I'm going to run this regression again. Excuse me. Once again, R squared doesn't change. Test statistic, which means the p-value doesn't change. Now my coefficient is a little bit higher now because now a 1 unit change is an additional $1 billion GDP. Now we're getting something that looks a little bit easier to work with. Right? Now, it doesn't really matter. Notice like the value is actually the same. So 1.38. 138, it's just moving that decimal, right? I'm just scaling that variable, okay? Any questions on anything there? I want to make sure I'm not moving too fast here. Yeah.
Oh, never mind. I guess we don't have any static commands on the exam. I was gonna ask if we would have to like scale it if we just wrote the number down and move the decimal ourselves.
No, so I might ask you questions like, I think there's one in the practice exam similar to this. Yeah, like if I scale income here, I might ask you a question like what's going to happen in the regression, but I'm not going to make you kind of run the regression, kind of scale that coefficient yourself. I'd ask you more about what's happening to like the size, right? Here we see it's increasing. Any other questions on this before we keep moving? Okay. So what if I include, so I'm going to just copy, paste this. So what if I had some imperfect multilinearity? So I think we'll use an example similar to this in a class. But let's say I now want to start including additional regressors or independent X variables in my regression, and I include population. Well, as my population goes up, what inherently is going to be happening to my GDP? Every person I add has to add something, right? So I know that these two things, you know, GDP is essentially going to be a function of population. So what's one problem that can occur if I have imperfect multilinearity? So it's going to increase the standard error. Now, we don't know which variable it's going to increase the standard error of. And in fact, that's a minimum. The minimum is that it's going to impact one of these variables. It could impact the standard error of both, right? So I'll run a regression here where we see if we just run these independently, and we kind of see what's happening to that standard deviation. Okay. So I'm going to run each one individually and then run these together. So we'll kind of compare and contrast. So let's see if we can get them all. Yeah. So notice here, my standard error, 0.0012, 0.0013. Okay, so it went up, but not a ton. Here I can have 0.0012. This is 0.0014. So my standard errors both did go up. Here, because they're relatively small, it didn't look like it impacted them that much, right? But they still both went up in this example. So it's always going to have imperfect multilinearity. It's going to inflate these standard errors. So why do we care, right? Well, I know that if I have a test statistic, right, We look at that formula sheet. How do I find the test statistic for a single slope coefficient? It's just going to be that slope coefficient divided by its standard error. So if this imperfect multicollinearity is causing the standard errors on my estimates to go up, what's happening to my test statistic? Larger denominator. If my test statistic is going down, what's happening to the area to the right of it? It's getting larger. So my p-value is getting larger, which means am I more or less likely to reject the null? Well, we only reject if that p-value is less than alpha. So I'm less likely to reject. So this is why we kind of care about the fact that those standard errors are increasing, because it's going to make it harder for us to be able to say there's a statistically significant relationship between these two variables. Even though inherently, we probably know, especially for GDP, that's definitely going to have an impact on life expectancy, right? And so if we have our standard errors impacted enough, maybe we don't see an effect, okay? So what is one solution to this that we talked about? So if I still want to include both of these in my regression, what's one way I can get around this imperfect multicollinearity?
Make one a function of the other.
So close, right? I don't necessarily make one a function of the other. One already is a function of the other. But if I think about writing out, like, let's say, oops, let's say I had GDP is some function of population. If I then divide GDP by population, dividing this by the population kind of cancels out that imperfect, right, that part of the GDP that was coming from that linear relationship. So what I can do, we said, is create like a ratio of the two, all right? You can do like a more complicated function, but often kind of as simple as we need is just kind of this ratio. So I'll take, what do we often kind of see reported? Not GDP, but GDP per capita. So I'm going to call this GDP per capita, right? Where I just take my GDP divided by my population. So I'm then going to say, let's regress life expectancy on this new GDP per capita variable. Okay. Where are we at? What didn't it like? Oh, I have to type more carefully. There we go. Okay. So now I've got kind of one variable that's kind of capturing the information from both, but I've eliminated this imperfect multicollinearity service. Okay. Any questions up to this?
Can you, what exactly is multicollinearity again?
So it's essentially that these variables are linear functions of each other, right? So in my example where it's like over or 65 or 65 under, anytime I know that over 65 is 1, 65 or under has to be 0. So there's going to be no variation that exists for every, like, those two will always be the same, right? So anytime you have the same, two variables have the exact same value pair, if you want to think about it that way, anytime x1 is 1, x2 is always 0. And anytime x2 is 1, x1 is always 0. Essentially, you've provided no additional information, right? Now, we don't dive into like the linear algebra that's going on behind the scenes here, but essentially that's going to cause some issues with us, some issues for us with our linear algebra.
See a function in your standard error, does that imply less?
It could, right? You know, it's difficult because we also have part of that coefficient in standard error is also capturing like omitted variable bias, right? So in practice, it's really hard to know exactly why that standard error is happening the way it is. Here, we're just building from a simple model. We're thinking about what I went from GDP once I included population. Like it could be like I usually in perfect multicollinearity, we kind of have to anticipate knowing something about like the intuition behind how these variables would be related. And I'm not gonna like expect you to like identify, like, there's definitely, you know, just, I might suggest if there is, what might happen to standard errors, what's one way we can solve it? Yep. What else do I want to do here? So let's do, we'll do this exact same regression. But now I'm going to add in some more variables. So what do I want here? Let's do BMI. Let's do, oh, what do we want? These are kind of all the same. So let's choose schooling. We'll do that. So let's do simply BMI and schooling. Right? So I think the schooling was like the rate of which someone obtains a high school education. Let me see. That can't be it. Let's look at it, see if there's something in this. Does it give us a code? Well, I forget exactly what this represents, so we probably don't want to use that. Let's just do. Right. Well, we just won't. We'll use schooling, but we won't focus on the interpretation of it because I can't remember. It's something like the rate of. I don't remember if it's high school or college attainment. It doesn't make sense for a high school because they're pretty low. So let's look at like. Oops. To sort the data here. Country. Okay. This is my way of cheating. I just want to see what the United States rate is. So, so 12 point. This must be the average years of education, right? So like 12 would be a high school degree. That's definitely what this is. So we can now interpret this. All right. So I've added these two variables in, right? I'm going to run this regression. So how would I start to interpret my variable? So GDP per capita, this gets to be kind of a weird one, right? Because remember, we had GDP was in what? Actually, did I take GDP or did I take my new variable? I think I took my new variable, right? Yeah, I took that new variable. So it was kind of taking the GDP in billions, dividing by the population. So here the units would represent kind of the $1 billion of GDP per person, right? So instead of a weird kind of unit to think about, I probably wouldn't ask you a question on something like this that had a unit that's kind of a little bit off, a little bit different. But on BMI, everything about this is just measuring points, right? An increase in BMI of 1, right? An average BMI in that country of 1 would increase our predicted life expectancy by 1. This seems kind of weird, right? So let's think of a story here of why this is positive. So we run this regression on BMI, life expectancy, and I'm just gonna, I know we have other things in the regression, but just for the sake of, here I'm gonna do BMI, and then we have these other variables as well, right? Remember, when we see these estimates from Stata, they'll contain the true effect of that variable, but if there's an important omitted variable here, they could also be picking up this, what we call omitted variable bias, right? So for us, what is X1? Well, this was the variable we included, right? However, if I think about countries that have higher BMIs, right? What's likely also going to be true? Now, we kind of captured a little bit of this with GDP.
So their quality of life is probably.
Their quality of life is probably quite a bit higher, right? Every family probably has more income. So we kind of captured that with GDP. But you can imagine, maybe it's not just income. Maybe it's that in countries where we see people have more access to food, right? They also have more access to better public health systems, right? So maybe the expenditures, in fact, let me see if there's, I can prove this to you. So we could do, where are we at? Yeah, I've got a variable that kind of represents this. But to make it an easier way to think about it, let's just say this is like the per person dollar amount the government is spending on health, right? So usually in data sets, you'll see things like health expenditures by the government. So it's likely in these countries that have high BMIs, the country is also likely spending a lot of money on healthcare, right? So these people have better access to healthcare. So if I had, we'll just kind of call it healthcare for simplicity. If I had included that in my regression, what would the effect have been on life expectancy? Countries that invest more in their healthcare system, what do you think happens to their life expectancy? Goes up. What do you think the relationship is between BMI of a country and how much it's spending on its health? Well, wealthier countries, right? These countries that are kind of having resources actually put towards healthcare as opposed to infrastructure, things like that, it's likely that their people have more access to food, right? Maybe even too much food. So I would expect there's probably a positive covariance between those two things. So just this one important omitted variable, what's it causing my estimate to be? Well, we didn't put a sign to this, but what's the variance on anything?
Positive.
So positive, positive, positive. The estimate I see is actually going to have a positive bias. So the estimate I see will be a little bit too high, which is why I can end up with it looking like having a higher BMI is leading to higher life expectancy. Now, it could also be the case that the effect of a higher BMI is positive. I mean, if you think about it, it's probably not linear. You know, if you have a BMI that's extremely low, right, malnutrition low, well then yes, having a higher BMI is going to increase life, but it could be capturing some of these important omitted variables that we don't have in our regression. Right? Once again, I'll try to lead you on the types of questions I would ask you. I wouldn't just expect you to like pick that healthcare expenditure variable out of the blue. I might even say something like, give you the actual output of the covariance between BMI and health expenditures, or BMI. There's probably other important omitted variables we have here too. So maybe it's that BMI is positively biased because it's also positively correlated with just access to food, right? Having larger access to food. So, but I would give you like that specific variable when I'm thinking about the specific omitted variable. I wouldn't expect you to just kind of pick one. Okay, is that clear what I'm saying there? Okay. All right, so what do I want to do next? We just talked about an omitted variable bias. Trying to kind of save this and I'll post this here. And I've got my code, so instead of me having to think through it, there it is. I'm going to copy and paste this over here. So I'm just going to generate this random number, comes from a uniform distribution. I could sort it, I don't have to. I'm then going to generate this small sample variable, which is going to be the very first 100 observations, right? I'm going to take and put a 1 in. That you don't have to have this code memorized. If you're just wanting to kind of copy it, this is what it is, right? If you're kind of following along. So what this is doing is it's giving me a smaller sample size, okay? So if I'm thinking about having a smaller sample size, I can think about the things that might do to my regression results. Now, in theory, if I have a smaller sample size, well, it's a different 100 observations, right? So it could be that my R squared changes, but in theory, if I could take, say, 1 million samples of size 100, and then 1 million samples of whatever I had, 2,800 or whatever it was, I should end up seeing the exact same R squared, right? The average R squared across all those 1 million different samples. However, having that smaller sample size is going to do something to my statistical significance, right? So I have the equation in the formula sheet. I'll make sure I show you exactly where this comes from when we go back to this, the slides, the screen. But our standard error is going to be the square root of the sum of the difference between our errors here, actual predicted y, right, and over n minus 2. Excuse me. And this is Yeah, we'll revisit this. So just to kind of make this point, if I have a smaller sample size, what's going to happen to n? N is going to be smaller. So what's happening to my standard errors? If I'm dividing by a smaller number and my standard errors are going up, what does that do to my test statistic? Decreases it. If I have a lower, a smaller test statistic, I'm like going this way. So the area in my tail is getting larger. So my p-value is going up, and it's going to be less likely I can reject the null. Right? So having smaller sample sizes, this is going to be true about any question I ask. Having smaller sample sizes will always reduce the likelihood you can reject the null. Always. Right? That's the effect it's going to have on individual coefficient statistical significance. That's the effect it's going to have on joint significance, right? It's always going to be its effect. So we can look and see, prove that to ourselves. So I'm going to run that code that we had before. Hopefully everyone was able to copy it down. I'm going to copy and paste that exact same regression, but I'm now going to add on, I only want to run this for when that small sample variable is equal to 1. So I'm only going to run it for those random 100 observations. So when I do this, I should see before, what was true about every variable in my regression before? P-values were like 0. It's really large tests, 17, 15, 24. Everything we could project and know at very high levels. So now if I run this regression, where I'm only looking at my smaller sample, and here, let me, just so I can kind of have this all on the same screen for you. I got to run them right next to each other. There we go. So here's my original starting sample. Notice my R squared is about 0.61. It is a little different from my smaller sample, but that's just because it's only one sample. If I were to take like an infinite number of samples of size 100 and 2800, it end up having the exact same average R squared. So my R squared should be about the same, right? Now the statistical significance on my variables, where all of them were highly statistically significant before, I could reject at any level. Now, even at the 10% level, which one can I no longer reject at all? But at 10% significance level, what variables could I reject the null for? All but GDP. All but GDP, right? P-value of 0 is 0.09 on BMI, so that barely makes the cutoff, right? But GDP per capita now has a P-value that's above 0.1. What about at the 5% level? Well, now the only thing I can say is significant at the 5% level is actually the schooling variance. So having this smaller sample size is always going to make it less likely we can reject the null for these slope coefficients. There's something else I want to point. Oh, what if instead I had said make this decision at the 95% level, but I didn't show you anything here. All you had were the confidence intervals. I probably am harping on this a lot because I might be likely to ask you a question like this or do something like this on PSA. If all you had were the confidence intervals, which of these variables would you say you can reject the null for, and why?
I think only schooling because it doesn't include 0, but I'm not sure what the 0.
Yeah, so when we think about these slope coefficients, excuse me, we don't want to forget that, well, doesn't matter which one, call it I, whichever coefficient we're looking at, we always start out assuming they're equal to 0. So what the confidence interval is telling me, I'm going to see some estimate for that slope coefficient. I'm going to build a confidence interval around it such that I'm saying, based off the sample evidence I saw, with 95% certainty, or at the 5% significance level, I could say, based off the sample I saw, the true coefficient value is somewhere in this range. So,
You say it's equal to 0 real quick. That means that there's no relationship between the two.
exactly. So we found from our sample that it was something other than 0, right? However, at that 95% level, these were all the possible values that true slope coefficient could be. Oh, sorry. So if this range doesn't include 0, I know that 0 can't be one of the possible values. I should be able to reject that value of 0, that assumption that I started out with. Now, if 0 is in my range, well, that could be one of the possible true values. There, I should fail to reject it. Right? So anytime my confidence interval, right, based off the sample evidence I found, I'm saying with this level of certainty, you think the example here is 95%, I'm saying 0 could be one of the possible true values, I'd fail to reject the null. So if we looked at that output, and just looked at our confidence intervals, you know, it's kind of small. Again, I wish there was a way to load the actual state output up. You can do it with the files, but so here, GDP per capita goes from negative 0.02 to 0.2. So it includes both negative and positive values, which means it also has to include 0. So I can't say that 0 isn't the true value, so I fail to reject it. Same kind of decision we made with the p-value. Look at the next one, negative 0.1 and 1.29. Once again, it includes 0, so I can't reject it. I fail to reject. Same decision we made with the p-value. 1.38 to 2.54, well, that only includes positive values. 0 isn't in that range. I can then reject 0 as a possible true value. Same decision we would have made with that p-value. So I might only give you confidence intervals from the state output just to kind of test you on that concept of what this confidence interval actually tells us. Any questions on that before we keep moving here? We got
Hypothesis that we always assume that the relationship is 0 to start out with.
always. We don't have to. So for this class, always. You can. So it's a good question. And we might change some things a little bit later in the semester, so it's probably worth at least thinking about. Let's say, what's the one? I'm going to write it down and I'll switch over just so I have this here. Let's do, so for that schooling variable, the lower bound was here, my upper bound was here, right? So we said we could reject 0 because 0 wasn't in that range. What if I had said, and I think it was like beta 3, I think it was the third variable that we used. What if instead of assuming it was equal to 0, I assumed it was equal to 1? Could I make a rejection? Well, my confidence interval tells me the true possible value somewhere in this range is 1 in that range. So I could actually reject it. So I can make rejection decisions for values other than 0. And honestly, there, it's easier to use my confidence interval because if I want to do it with my p-value, what do I have to do? Well, we kind of actually cheated because our actual test statistic, if you go back in the slides, the very first time I introduced it, I think I wrote it as gamma, right? But here, this was going to be our assumed true value. We just said that this is always 0 for us. You can put in 1, 2, 50, whatever, but that would change your test statistic, which then changes your p-value. So when you're running that regression in data, it always defaults to 0 when it calculates the test statistic. I'd be lying if I said I can remember or if it's even possible. I am sure it's possible just based off its capabilities that you can change the calculation. Like there's probably an option where you can change the, like just like you can change levels to 99, 95, 90%. You can probably change what that assumed coefficient is. And there are tests where you can do, but if we got the confidence intervals, we don't really need to rerun and recalculate these test statistics because the confidence interval already tells us these are the values that you'll fail to reject. So if you assume it's 1, you'll fail to reject it. If you assume it's 3, you'll fail to reject it. What if I assume it's 2? Well, 2 is in my range. So there I would actually, fail to reject it, right? So I could test, like think about any hypothesis. The only ones where I'm going to fail to reject are for all the assumed true values in the range of my confidence interval. Anything outside of it, I know I'm going to be rejected. If 0 is outside of it, I know I'm going to reject 0. But to be completely honest, This is just half to zero. We can do these other. I won't do that on an exam. I'm only ever going to use the default of zero, but yes, you can. Any questions on this before we keep moving here? Okay. This should seem hopefully easy at this point, but before I kind of keep moving, let's say, so the results we have here. So I have life expectancy, and I had, this was that GDP per capita variable. We had BMI, and we had this schooling variable. Okay. So the values that we found here were, and I'm going to egregiously round some of these, but well, I'll just go to the second decimal. So this is what, 0.089, 0.59, and just to make this easy, 0.09. And then schooling, we had 1.96, right? So I could ask you to make predictions for this life expectancy variable, given some output from Stata, because as long as you have the coefficients, and I said, okay, let me look here, so I'm not choosing crazy values. So let's say I have a GDP in billions, right? Because we scaled that variable. Let's say my GDP in billions per capita is 10. Let's say the average BMI, that's what, does 20 make sense? I forget the range of BMI these days. I haven't cared about mine too long. So say it's 22, right? And let's say the average years of schooling is 13 in this country. How could I make a prediction for what that country's life expectancy would be? All I do is use these coefficients, plug in these hypothetical values for my X variables, and now it's just kind of a linear equation, right? Just getting that entered into my calculator. So if I ask you to make a prediction, given some Stata output for a hypothetical observation, these should be easy points.
Multiply them by the coefficients, right?
Yep, right? So I guess technically,
No, I just want to make.
yeah. Yep. Now, the one thing that's easy to get a question like this wrong is to forget your intercept, right? You need to remember that your predictions always, because how would we interpret the intercept in this example? When everything's equal to zero. So if GDP per capita is zero, BMI is zero, this is weird, right? Schooling average is zero. We know that never exists. Like the data, when we come up the visual, like the 0 points over here, all the data might be over here, but we're estimating that line of best fit. It does have some starting point. We may not ever see data points down here where it starts, but that line, right, mathematically, the line has to have an intercept somewhere. So that's still how we're going to interpret these intercepts. And they're always going to have to get added in to our predictions. So we don't want to forget those. Okay. Any other questions on this before we keep? Excuse me. Okay. Yeah.
So question, so say you're like only increasing GDP per capita by 1 unit, right? And then you're calculating your new intercept for your life expectancy. Do you still add like your BMI or your schooling coefficients, or are you only increasing that GDP per capita?
So if I asked you about what the impact on the predicted value was of just one, well, then the amount it's changing it is just going to be whatever that slope coefficient is, right? Because it's going up by 1 unit.
Yeah.
When you're making your actual prediction, what you would do, well, if everything would be the same, except like in your example, you're saying GDP goes up, per capita goes up by 1 unit, you would basically have whatever your life expectancy was before, right? It would have all of this. If you then predicted life expectancy after this goes up by 1 unit, what's the only change in this prediction? It's going to be exactly what you found before, plus what? If this goes up by 1 unit, that coefficient, right? So yeah, the difference between those two predictions would just be That's why we interpret the coefficient that way. Because it's literally telling us, if you make predictions, this is how much a 1 unit change in this variable would increase or decrease that prediction. Oh, and you guys can't, oh, sorry. There we go. Okay. Any other questions on this before we keep moving here? Okay. It's another concept I want to make sure we do. Let's go back to.
Is there gonna be a large emphasis on homoscedasticity and heteroscedasticity?
That's a good question. So let's say I think that there's some heteroscedasticity in some of these variables, right? So I'm going to run this regression and then run that IM test, right? Now, we talked about heteroscedasticity because it becomes a lot more complicated with these multiple linear regressions, right? But we talked about it with simple linear regressions. And the way that we would do this, oh, I got asked a question and forgot where I'm at. So all I did was run that IM test command. That was the test that we had for heteroscedasticity. I think I went in my soapbox. There are other tests, right? If you Google them, you'll find one, and many of you use them, but it's not giving you exactly what, it's giving you an amalgamation of several different types. We are just going to use this test for heteroscedasticity, right? It's kind of our most reliable test, especially when we're dealing with these simple linear regressions. So it ends up telling me a test statistic and a corresponding p-value. This is actually kind of a weird one. I'm glad it worked out to be the exact way that it did. Because at what level? So we always start out assuming that our errors are what? Anytime we're testing to find something, we assume the opposite is true. So when we were testing to find if there's an effect between this x variable and this y variable, we started out assuming that the effect was 0. Here, if I want to test whether or not there's heteroscedasticity, I'm going to start out assuming almost so. Can I reject homoscedasticity here? Or if I can, at what levels? It's a weird one. So at a 10% significance level, would I reject it? Yeah, it's 0.05, right? So I would say at the 10% level, I'm rejecting that the errors are homoscedastic. I think they're heteroscedastic, right? In which case, what do I need to do? We said, I'm going to use this. Actually, it's going to have to be after my conditional statement. Robust command, right? So if I use that robust command, notice kind of what's happening to my p-values there. Well, whatever variables it was heteroscedastic, it's going to kind of change their p-values. Notice my GDP per capita must have been where my heteroscedasticity was because it fell quite a bit, right? So we can account for that heteroscedasticity, but the only thing I might ask you to do is I might give you this test result, and then you kind of have to know we start out assuming they're homoscedastic. Right? Now this is a weird one. I said it's kind of good because can I actually reject at the 5% level? No, right? Our rejection decision is that it's less than alpha. It's exactly equal to alpha, which I wouldn't give you one like that in the exam because that's kind of tricky, right? Like it's right on the edge, right? But the technical correct answer would be no. We failed to reject. It's not quite less than our alpha. Something else. Did that answer your question about?
Yeah, I just wanted to know if there'd be like anything on these. So the chi2 is your test.
Yeah, we didn't talk about it's called so we have like the student T distributions, normal distribution, F distribution. It's technically called the chi-squared distribution. It's got, deeper we get into this class, you'll see more and more Greek letters kind of start popping up. But we don't really care about where it's coming from. Anytime I give you this, I will tell you what that corresponding p-value is. Yep. Trick question, because I would have honestly probably forgot about heteroscedasticity. What I wanted to go through next is thinking about, let's say I wanted to, we started out with an example like that at the beginning of the class. So let's say I want to add in some stuff. So I'm going to do, what's this called? Infant deaths, right? I would also maybe think that as time progresses, countries, like every year goes on, life expectancy goes up. So maybe I'll add in year. And then I'm also going to add in this alcohol consumption, right? So I'm just going to take this smaller sample, so I'm just copy and pasting that regression we had before. But now I'm going to add in year, infant deaths, and this was like the average alcohol, I think it's like liters per something or other, alcohol consumption, right? So I've added in 3 variables. I can then run this regression. So I'm going to run the original one, just so we can kind of compare and contrast. And now I'm going to add this one where I've added in 3 additional variables. So what's happened to my R squared? Ooh, it's went up quite a bit. So this probably isn't crazy. Why did this go up quite a bit? Which of the variables that I added in is probably a really good predictor of what happens to average life expectancy. I'm now controlling for the number of the proportion of infant deaths. Infant deaths going to be really small values. What's that going to do to my life expectancy? Pull that way down, right? Well, I'm now controlling for that. I'm controlling for the fact that some countries might see higher infant death rates, which is inherently just going to decrease. So now that I'm controlling for that, my life expectancy is kind of telling me more like, okay, given that like you can get past those first few years of life, then if you're living in this country, how many years can you expect to live? That's probably a lot more of what we want to know, right? We know that in foreign countries, we're going to have a lot higher rates of infant deaths. So inherently that life expectancy will be lower. But we want to know, given that people kind of make it to adulthood, how long can they expect to live in this country? And or that might be the question that we want, right? So we now get kind of control for that. So R squared went up quite a bit, but can we say it went up at a statistically significant level, right? Because we've added in 3 variables here. So we're doing joint significance tests. I might give you output like this on the exam and then ask you, similar to like the quiz or you may see the practice problems, what's the F statistic associated with this joint significance? Because I want us to kind of think through what's going on in that F statistic equation. So we said anytime we have a test statistic, we're starting out with like sample something. So we had before, maybe it was a sample mean, maybe it was a sample coefficient, right? But that first thing is always going to be our sample statistic. So here when we're testing for joint significance, we're essentially saying, did adding in these additional variables have additional explanatory power? Or did they increase that R squared? So we're looking at the difference between that new unrestricted model where we included all the variables and the restricted model where we were leaving those 3 out. We're then going to scale this by, or divide it by, well, we know that as we add in more variables, what is always going to be true about this difference? My unrestricted R squared will always be, my unrestricted model is the one that has more of the variables. So my unrestricted R squared will always be higher, right? So that's why we said we had to use the F distribution, because that was where we're not actually looking at a 2-tailed test. We're actually only looking at the right tail now, because we know that this has to be a positive change. So because we know that this has to be positive, well, if we just start adding in a bunch of variables, we can get this difference to be larger and larger and larger. So we are going to kind of penalize ourselves or scale down that difference in the R squared by however many additional variables we've added in, or however many additional restrictions we have. That's what Q represents.
Wait, you said as you add in more variables, it's the difference? It'll decrease, right?
So if I start adding in more variables, my unrestricted model, instead of just 2 variables, I add in 3. What has to be true about my R squared? It's going to be a little bit higher. So that gap between my original model, if I just start, the gap will be higher, right? So if I think about, let's say, I run my naive regression and I find an R squared of 0.5. I then add in 1 more variable. What's going to happen to my R squared? Well, now you can kind of think of this, my first unrestricted model, maybe it goes up, right? But even if I add in a second variable, even if it only goes up a little bit, it has to keep going up. So that gap, I know my difference is going to be larger, right?
I thought your unrestricted was all the variables.
It is.
So if you have all the variables and you restricted, let's say you have like 7 variables for your unrestricted.
Mm-hmm.
Or yeah, for your unrestricted, and then for your restricted, you're including 3 variables.
Yep.
Okay. okay, so that R squared value is gonna be less than if you included four variables, so that difference would decrease.
Yeah, if you're thinking, the way you're describing it, though, is going from a lower number or a higher number of restrictions to a lower number. Right? So if you're going from,
Oh, yeah, I get it.
yeah. So yeah, if I start to look at a smaller number of restrictions, then yeah, that gap in between those two would get smaller.
Yeah, so when you say smaller number of restrictions, you mean that include more things, so you're gonna have.
Yes, yeah, sorry. So this is just going to be the difference in the variables between these two regressions, right? That's what Q represents. So we then said we're going to scale that by, not scale it by, but here, what our R squared from the unrestricted model was, and then N minus K minus 1, where K was the number of total variables in what model. Well, one way you can kind of remember this, K here, it's the number of restrictions in your, or sorry, number of variables in your unrestricted model, okay? So this is going to be the F statistic that then gives us a p-value to determine, did adding these three variables in have some joint significance, right? We saw the R squared went up a lot, right? That doesn't necessarily mean, if we had a small sample size, maybe we actually don't end up with statistical significance here. So let's think through. So I'll go here and I have stats. Oh, what do I have? I have these three variables. It's not what it is. What is it? H stat IM test. Forgetting the actual. Oh no, never mind. I'm just showing you the easy one. Okay, so we'll just use test, right? We're going to use this test to do joint significance after we run the model, and I'm going to do a joint significance test on these three variables. Okay. So I'm going to run this line of code, and it says, well, look, that F statistic is huge, right? And that kind of makes sense. We did see a pretty large increase in that R squared. So not only was it a large increase, its statistical significance is really high here. We can reject the null at any of our conventional levels. What's the null? That these added variables had no additional explanatory power, that they weren't really changing the R squared in a statistically significant way. We can reject that, right? Very easily here, p-value 0, okay? Now, maybe what's a more interesting one, I'm gonna just go out on a limb and guess if we did this exact same thing. So to your point before, let's say now I take out this infant deaths and I just added in the, make sure there's no spaces, there we go, year and alcohol consumption variable. Well, now my number of restrictions, right, is no longer 3, it's now 2, right? So this might, it's going to decrease. So what's that going to do possibly to my F statistic? Could increase it. However, if this restriction that I left out was increasing the R squared a lot, then maybe this gap is now closer, right? To your point earlier, when I have fewer restrictions, it's likely that this gap is going to also be smaller, right? So I've got kind of competing effects. This goes back to, the age-old, there's the running joke in econ departments, like, well, what's the answer? It depends. It always depends. So there's always like competing effects. I would, which one's larger. So we can't really, with our intuition, guess what's going to happen here. But if I were to run this, what I'll see is, okay, well, my R squared from that original regression way up here, which was 0.61, this is only 0.63. When I just added in year and alcohol consumption, I left out that infant deaths. That was the variable that was really driving that R squared up. So these added variables did increase my R squared, right, 0.61 to about 0.63, but did they do so at a statistically significant level? Well, my F statistic is 2.6, p-value is 0.075. So what levels could I say that these added variables are jointly significant or had additional kind of explanatory power of that Y variable life expectancy? Only at 10. That p-value is only going to be less than 0.1. It's not less than 0.05 or 0.01. Yep. So at the 10% level, I can say that these added variables had joint significance. They allow me to have additional explanatory power about my Y variable life expectancy. But I can't reject that. I can't say they have any additional explanatory power at the 5 and 1% significance levels. And just always floating in behind the scenes here, I always say things in the terms of significance levels because that's always kind of usually what our output is. But what 10, 5, and 1% significance correspond to what levels of confidence?
95, 90, or
90, 95, 99, right? So being able to say, we could say here, we were able to say that it added some explanatory power with 90% confidence. We can't say it quite with 95 or 99%.
why don't we ever say like 93?
You know, I'm not old enough to know why we chose these exact three. I mean, it kind of makes sense, right? Like, they're good cutoffs. 90, 95, 99. Like, why didn't they choose? Although I've always kind of debated, like, I mean, this is a more philosophical discussion, but like, to me, like the 85% level is still pretty, I mean, we should not be ignoring something. If we could reject it at, just because we can't reject it at a 90% confidence level, we can reject it at 85. Well, that seems silly, right? It's still pretty significant. So if you'll see, sometimes people report, I think it also is a little bit like discipline dependent. So like I've seen papers sometimes where they use the 92.5% level as a cutoff and 97.5, like they kind of do 2.5 percentage jumps and report it in that way. Anything you look at in economics, that's just the convention. And it's not just econ. Yeah, yeah. That's a good question. All right. Any other questions on this? Yeah, one more thing I think I'll do before we end here. So let's think through this. So let's go back to this model where we had, well, I don't know if we're going to get it, even if we do it this way. We'll try it. If it works, it works. If it doesn't, I've got another one we can use. So we're going to just kind of do that same joint significance test down here. Oh, actually, no, I don't want to do this one. Forgot we're looking at the smaller sample here. Let's do the one that we just did, right? So we had statistical significance at the 10% level, but not the 5 and the 1. Well, what happens if instead I run this exact same joint significance test, but for the entire sample? So I went from now a sample size of 100 to a sample size of like 2,800, I think it was. So what's happening to my number of restrictions? Nothing's changing there. Still going to have maybe the same gap, right? But my sample size is going up. My sample size goes up here. What's going to happen to this fraction? This denominator is larger, so this goes down. Now this denominator is smaller, so my F statistic will go up. That's going to do what to my p-value? Well, if my F statistic is going up, it's making that area in the tail smaller, or my p-value is lower, however we want to think about it. So that means I'm actually now going to be more likely to reject that null, right? So we can kind of see, you know, I might ask you questions like this where I say, assume that you got more data and you ran the same regression. What would you expect to happen to the F statistic? What would it be more or less likely you can reject the null, right? Maybe it's even multiple choice, and like, you know, some of the answers are, you know, it's like fill in the blanks, and one of them is, you know, does it go up or down or increase or decrease? So here, we can kind of prove this to ourselves. When we run this with the entire sample, our test statistic is no longer 2.6, it's 25.7, right? So you can see how dramatic an effect. God damn it. So if we run this, right, regression with the whole sample, we see a much larger test statistic of 25.7. Now we can say at any level that we can say there's joint significance of that invariant, right? So knowing the effect of that sample size on our F statistic or our joint significance is important too. But it's the same thing as our individual significance we talked about earlier, right? Higher sample size makes it more likely I'm able to reject the null, increases my test statistic. So we kind of started out with an example where we had multiple groups. I might Tuesday revisit that with this one because like we've got regions, we could do kind of something similar. But probably Tuesday's class, I'm hoping that it gives you more time, you know, it's fall break. probably got fun things planned. But if you're able to kind of look at those practice problems, really Tuesday's class, I expect to be just a lot of that practice game, right? So I think it'll be highly valuable for the exam. I also, at that point, will have the exam finalized, so I can kind of speak to, I'm going through these things that I know there might be questions really similar to, okay? Other than that, your quiz is due by the end of the day tomorrow. Your problem set's due by when? So if we look here, that problem set's due Tuesday. I think I even have it set to be before class. Yeah. So turn that third problem set in before we start class on Tuesday. Probably won't get them graded before the exam, but I'll at least kind of get started on those. Also, for this section, everybody's first two problem sets should be graded. If for whatever reason, I looked at the grade book, so I know that they are. But if there's any questions or anything you have with those first two problem sets, please let me know. I'm going to get, because they're great, I'm going to get solutions posted to those. So if you run through the quizzes, run through real practices, you run through that practice exam, I'll put up the solutions to those. They won't be as helpful because a lot of that is like state of work. But some of the like open-ended question parts of those problem sets, it might be valuable to have those solutions. So as soon as that due date passes on the third problem set, I'll also post the solutions to that after class on next Tuesday. So you'll have that as well. Okay? Any questions for me? Was this, hopefully, did you feel like this was beneficial at all? Yes? Okay. I always never know what to do. I'm better at knowing I can run through this organized. But I also think doing things on the fly and having people ask questions on, I think this is actually really valuable. We've got to a point where hopefully I have enough understanding of the concepts and also enough kind of data where you can really start to kind of combine these two, and it helps make both of them make a little bit more sense. So, once again, fun, safe weekend. I'll see you guys on Tuesday.